In this context, of course, the steady state, given that here the game is played by the collisional map, so it's clear that, let's say, the condition for a steady state is that, let's say, rho star is a steady state if epsilon rho is equal to rho. So, of course, this is the condition for the steady state. Now, so and of course, since, let's say, the evolution is, let's say, actually, this is probably something slightly more important than, I mean, the property of Markovianity can be expressed also with the property of semigroup. So that means that, suppose that, again, it's a formality, but let's say, suppose that you say rho, let's say, n after n collision can be written as a map, lambda n acting on rho 0. Now, the fact that the collisional map is written like epsilon, then epsilon, then epsilon, and so on, this is telling us that this map obeys a semigroup condition, which is that lambda n can be written as lambda, say, n minus m lambda m. So you can, let's say, compose the maps and they obey a semigroup condition. Of course, it's just a semigroup because the dynamics is open, so you don't have the inverse. So, so this is just a semigroup condition. And this is actually, I think, equivalent to Markovianity. Having Markovianity is the same thing of having the semigroup property of the collisional map. And this is the condition for steady state, which more than that tell us that epsilon to any power of n is equal to rho, to any power n of rho is equal to rho. So this is the condition that the state doesn't evolve. Now, a property is that in general, epsilon of, let's say, something can have multiple steady states. So you can have a map that can have multiple steady states depending on the state. You can have multiple solutions to this equation. And so depending where you start, you can end up in different steady states. Now, based on this property, systems for which, let's say, rho star is unique are called, so if you have a system for this, you say that your system is ergodic. This is just terminology, but it has a, let's say, again, a meaning that is related to the physical, again, to the map, to the physical situation. Because, for example, thermalization is this case. Suppose that you are, let's say, you are treating in a collisional way a system in which the bath has a certain temperature. The steady state will be the thermal state at that temperature. And so this is an ergodic situation. Even more, you can say that if whatever initial state rho n, let's say, whatever rho 0 you take after a certain number of collisions, you end up always in a steady state. You say that this is, let's say, even more than ergodic, this is mixing, which is, let's say, the situation in which you will arrive to the same steady state, no matter where you start. And okay, let's see a particular example in which you don't have ergodicity, and an example in which you don't have ergodicity is exactly the case of before. So suppose that, for example, you take the previous case and you say, no, this is worse. You take a G delta T equal to pi and G Z equal to 0. So in this case, you can easily see that your rho prime equal to epsilon rho become P minus C minus C star 1 minus P. So in particular, you see that any row taking, let's say, the form, any row, let's say, defined by P 1 minus P 0, 0. So any state that doesn't have coherence is a steady state. So you have multiple steady states. So in particular, this is non-ergodic. This map is non-ergodic. And also you can have, for example, suppose that you take your rho 0 to be plus, plus. Then in this case, where, okay, plus, of course, is 1 over square root of t, 0 plus 1. So you take this, and it's easy to verify that epsilon on plus minus, where of course the minus is with the minus here, is equal to minus. So you see that in this case, you never reach a steady state. If you start from this, you keep oscillating from plus to minus, from minus to plus, and you never reach a steady state. So in general, let's say the collisional framework is quite rich. You can, let's say, devise maps in which you never reach a steady state, or you reach multiple steady. An example is in the micromeasure, where depending on the initial conditions, you can reach like states that are even pure, as I was mentioning, or states you never reach a steady state. It can happen. So essentially, since that is very dramatic, because as I said, the micromeasure is the case in which, let's say, etas are qubits, and let's say the system is, let's say, an harmonic oscillator. So in the very first approximation, you can, let's say, engineer a situation in which the energy on the harmonic oscillator keep growing forever. Of course, then there are also, let's say, other source of, let's say, noise and so on. So this is not what happens in an actual micromeasure, but at least theoretically, you can, for example, never reach a steady state because the energy grows forever. So yeah, so let's say the possible scenario that you can describe is quite rich, and you can describe very different dynamics. Comments? Then we switch gears a little bit, and we go to do something slightly different. Okay. So now the goal become to start to describe, let's say, the equations of motion. So the idea is that we want to make a connection with the actual physics, if you want. So we are not satisfied by, let's say, doing the collisional map and compute the updated density matrix and then send a new one. So we want to go a little bit more, let's say, analytically. So we want to get the equations of motion let's say, implied by the collisional map. So essentially what we are going to do is the following. We start from our collisional map. So let's say now, I should have asked 30 minus 45 and so on to the pads rather than, because I'm not sure that they will endure for 45 minutes, but okay, let's see. So we start from our rho n equal to epsilon rho n minus 1. So here, as we stressed many times, what we have to realize, let's say, is that the dynamics is intrinsically discrete. So in order to get some equation of motion, at a certain moment, we want to make this, so let's say here the dynamics is intrinsically discrete. And so we want to work with, let's say, delta t small. Now, I will clarify better what I mean by this. For the moment, let's assume that delta t, it's small but finite. We will see that try to send really delta t to be infinitesimal will bring complications. But this is something that at the very end, if our purpose is to make connection with, let's say, standard open quantum systems, is something that must be faced. Instead, if you have in mind circuits like suggested before, you could be happy with just a finite evolution dynamics. But let's say our final goal is to, at least to make connection with standard open system, is to arrive to something like d rho over dt. So we want to arrive to some equation of motion that at the very end will look something like that. So if you want, in this part, we, as I said, we will look for some equation of motion in which we will have essentially two regimes. One will be to talk about delta t small. And so we will replace this d rho over dt with something like delta rho over delta t. And we will assume that delta t is sufficiently small such that we can do perturbation theory, we can approximate the collisional map. The other, which will be more, let's say, complicated, will be to really send dt to 0, and so get d rho over d. But let's start first with this that is more straightforward. So, okay, so so with this in mind, let's start with our evolution operator. So un equal to, let's write it in this way, e to the minus I h naught plus vn delta t, where I'm putting h naught, I'm putting h naught equal to hs plus hn. So the two free Hamiltonians are there. And okay, let's assume, as I said, that delta t is sufficiently small. So we do an expansion up to second order. Let me put this within quotation because will be not really a second order expansion. We will see what I mean in a second. And then actually the motivation for this strange expansion will become clear later. Much later, probably even tomorrow. So in this expansion, un become almost the identity, of course, minus I h naught plus vn delta t. And then here I do a little bit of cheating. Square delta t square. So the cheating is that I'm doing a quote-unquote second order expansion because at the second order, I'm considering only the contributions coming from V. I'm not including H naught. If you want, the reason is because I'm assuming, and we will see, as I said, probably tomorrow, the reason for this weird approximation, if you want, the rationale is that, in a sense, n is much greater than H0. Now here, this should ring a bell and should make people super unhappy compared to what we said today, right? Because today we said that all the machinery in order to do open system is to assume a small interaction. Here I'm even saying that H naught is completely irrelevant at the second order. Where is the caveat? I'm really, let's say, am I violating the prescription that Jamil gave or not really? And if not really, why?
Since the particles are leaving, you are not strongly coupled.
Exactly. This is exactly the point. I'm assuming that the interaction is strong, but just one particle at a time. So this is not violating the prescription of today. It's a different framework, and we will see that it makes
violate it. I think you need to put delta T large.
Probably yes. Probably yes. Yeah, I would say yes. But it's not what you want in any case, because you want to go to go to delta T small. And actually, we will see that you are in the right spot, saying that I should put delta T large to really violate. But also the fact that, let's say, here I have a single mode at a time. So if you want, I could say in some sense that the interaction is by construction weak, because among, if you want, all the modes, so to say, of the buff, just one is interacting at a time. So in a sense, it's by construction weak because it's one mode at a time. Please.
In this case, V represents interaction.
V is, okay, an example of V is what we wrote before. That was minus or plus, I already forgot, G, sigma plus, sigma minus, plus admission conjugate, plus GZ, sigma Z, sigma Z. This was one example, yeah.
H dot is
the free Hamiltonians, which are the two free Hamiltonians for the system and for the buff. Okay, so yeah, so far let's take it, then will become, say, more clear. So now that we have the prescription, we can, let's say, compute. So sigma n, the full state, is given by, as we said, un sigma n minus 1, un dagger. And here you do all the expansion. And okay, here we need to be careful. I mean, it's a simple computation, and I'm gonna skip, but let's say what we get. So here is important to do this and do this. Let's say you plug this into here, this into here. You do the expansion. You keep, of course, only terms up to delta T square, but to stay with this, you, at the order delta T square, you keep track only of V. So terms that are delta T square, because there is an H naught and a V, are considered negligible. So you do this, and finally, yes, okay, I think I can write directly the final formula, and then we talk. Okay, so this is what I get. We already see something that should look familiar, right? So we see that there is some part that really look like a sort of, let's say, Schrödinger-like evolution. And then there is here some term with a plus here. So this is actually an anticommutator.
Okay.
That looks very similar to what we got before. So now, in order to go ahead, okay, by the way, if people like here, you can also write this. I mean, it's not really usable, I would say, but just for curiosity, let's say that if you don't like anti-commutators, you can write this as one of the two Vn sigma n minus 1. Yes, everything. So if you prefer, there is this alternative formula, completely equivalent. People always stay with the others, but the formula. Are there questions? I don't think I have to go through the derivation. Is really a simple exercise. You just have to take care of, let's say, get rid of all the terms that are not relevant with the regime of the approximation that we're doing. Now, what is the next step?
Divide by delta t.
But okay, no, but let's try to suggest something a bit better. What is sigma n?
It's the whole state.
So
Yeah, you need to do a partial test.
okay,
Sorry.
this is better, right? I mean, yeah, divided by delta t, yeah. Which is true, I mean, we have to divide by delta t.
No, yeah. I'm sorry for this.
No, thanks.
I know that I'm not in high school anymore.
Well, this raised something about the lecture, so probably was too low level that people start to say, okay, I should go with this suggestion. Okay, good. So, of course, I mean, so sigma n minus 1, how it is? So before the collision, this is
UN minus.
no, wait. Let's say, what is the state of the full?
Is the state of n minus 2 and eta.
Correct.
Eta.
Correct.
It's a string
Perfect.
of etas.
Perfect. So the state
Not eta.
before, no, sorry, this is not an operator. Rho n minus 1 tensor eta n.
Yeah.
So when the collision n is arriving the n ancilla and the state is in a given state. Then we define delta sigma, no, we define what delta sigma n is rho s n, so after the partial trace, minus rho n minus 1 tensor eta n. Okay? So now we can trace out the ancilla, trace out here. Again, this is a very simple exercise. And all in all, we get now we do the division by delta t, and we get minus I HS plus trace of Vn eta n. The trace is over n, of course. Rho n minus 1 plus delta t trace over n, and this trace is still not so beautiful. Vn rho n minus 1 eta n Vn minus 1 over 2 Vn squared rho n minus 1 eta n trace. And I have defined delta, coming worse and worse, delta rho n equal to the trace over eta of rho s n minus rho n minus 1. Okay, so this is becoming much closer to a form that we like, but still, I mean, do you like this expression? Not so much, right? Because we still have essentially eta everywhere, so we would like to get rid of that. It's still an equation that Formally, we have traced it out, but we didn't. So this is not yet in an Inbladian form, which is, so if you want, is not yet an equation for the system without essentially forgetting what happened before. So we need to suffer a little bit more, actually quite a lot. No, not so much. So in the last, okay, so let's say that in the last 15 minutes, we are gonna cover the first way to get an Inbladian form, and then we will see how to improve it from tomorrow. By the way, people there can still see, yeah, maybe, yeah. Okay, so this is our equation. Okay. Okay, so let's see how to reach okay, well, to reach an Inbladian form, there is a first approach that is really, let's say, simple conceptually, but a little bit like an overshooting. So the idea is that we will do the conceptually simple one to start with, and then let's say we will improve it. So in principle, you can make this guy looking as an Inbladian form by saying, okay, let's take a spectral decomposition for eta. So let's assume that we know perfectly the state eta that is arriving, which again, in a collisional setup, we could say that is not so crazy because you assume that you have perfect control on everything. So you can probably say, okay, it's not so crazy, but still an overshooting. And so let's assume that you know that eta can be written as a summation of p, k, k. Now, out of this, you can plug this information into the game, and you get this. So delta rho n over delta t is equal to, okay, so minus I, okay, let's say this part I don't touch it. I mean, it's a very simple, simple thing. HS plus, I mean, taking the trace over this, but I write it because it takes less space, but it's really triviality. Vn eta. This becomes simply a summation over pk of the matrix element kk. Rho n minus 1. And notice that, I mean, this is absolutely Hermitian. So this is describing the Hermitian evolution. And in particular, this is what Jamir was before calling the length shift. This change is, if you want, the first contribution to the dynamics given by the bath that doesn't break unitarity. And then you get the real, let's say, dissipative part, in which you get summation over summation over k and k prime of L k k prime rho n minus 1 L k k prime dagger minus 1 over 2 L dagger k k prime L k k prime rho n minus 1
pass, and they close the tiles. Delta T.
Yes. No, no, I'm absorbing here. And sorry, and A prime is becoming square root. My gosh. Yeah. Square root of the A square root of delta T matrix element A prime Vn A. Okay, so this is finally a Lindbladian form. We have our unitary evolution. We have our jump operators that enters here and induce the non-unitary part of the dynamics. So this is a Lindbladian form in which, let's say, we have the jump operators that are, let's say, this is what keep remnant of the open dynamics, because what enters are the matrix elements of the interaction Hamiltonian over the states of the ancilla. So this is, if you want, Lindbladian form. Now, I think we can probably more or less stop here. Let me just, let's say a few words about what we are going to do. Now, what we're going to do is essentially to recognize that this is definitely an overshooting, in the sense that this is assuming that you know, let's say, perfectly the state of the ancilla, you know all the k's that enter in the matrix, in the spectral decomposition, and you know all the pk's, so you are assuming a lot about the ancilla. And you will see that it's not, this knowledge is not necessary. What you really need are just, let's say, the first and second moments of the Vn operators over the ancilla states, so you need less information. And that will bring exactly to an equation like the one that we derived this morning in the open system formalism. Still, this is not a differential equation. Still, let's say, a finite difference equation. And we will see that passing to the continuous limit requires some attentions. After that, I think we will see some example and some dynamics. Yes, and then we will move to the other part, let's say, how we can start. So far what we did was something that at the very end looked not so far from what we did this morning in a conventional way, the end point, but still the dynamics is intrinsically discrete and so on. So what we will do later is how we can get this description starting from a genuine open system setup. I think we can stop. So comments, questions, complaints.
So for sure comment by Marathon, because we have it coordinated. Basically, the details of these calculations clarify a lot of what we have done this morning.
Yes.
Frankly, without this, maybe it would be quite hard to reconstruct what we've done. So I would almost suggest to first study this and then go back on what was in this part, because this is much more linear, honestly.
Yeah, it's very simple. It's very, very simple. If you want, there are no approximations. The approximations we will see are all under the carpet. They are in treating an open system like a bunch of ancillas that are coming.
Yeah,
that is
sort of it.
Exactly. That is all the approximation. But once you accept that crazy viewpoint, then all the rest goes. There is still, okay, no, we have to comment about this weird idea that we throw away H0 and we kept Vn at the second order. That sounds a little bit shaggy, and we will see why. But yeah, I agree that at the end, once you accept this viewpoint, it's very clear how to get it. Okay, so see you tomorrow, 9:30, right?
Yes, 9:30.
Okay.